Hello students, so today we will see the part 5 of the solutions theory. Disclaimer, the images, text and other materials used in our presentations are for educational purposes only. We respect the intellectual property rights of the original creators and owners. If you are the owner and have any concerns or issues, please contact us at sathee@iitk.ac.in and we shall remove the content immediately. Please note that parts of the content may have been generated using generative AI, which is experimental. In this lecture, our objective would be to describe some of the colligative properties related to solutions, and we will try to correlate it with the molar mass of the solutes. First of all, we will see that what are colligative properties and how we can determine the molar mass from it. Second, we will see the first colligative property, which is relative lowering of vapor pressure, also known as RLVP. Then elevation of boiling point, and at last we will see some examples. First, what is colligative property? So colligative properties are the properties which only depend upon the number of solid particles, and it is not dependent upon the nature of the particle present in the solution. So colligative here is derived from a Latin word which means together, okay, and ligar means to bind. So binding together means colligative properties. What happens when we add a solute which is non-volatile in nature to a solvent? The resultant solution will have a lower vapor pressure as compared to the parent solvent. As a result of this lowering of vapor pressure, there is a change in various properties of the given solvent, and these properties are studied under our colligative properties. What are these properties? First is relative lowering of vapor pressure of the solvent. Second is depression of freezing point of the solvent. Third is elevation of boiling point of the solvent. And last one is osmotic pressure of the solution. So the main idea to put this slide here is that it is independent of the particle, means the lowering of the vapor pressure or the change in the colligative property is independent on the nature of the solute. It is only dependent upon the number of solid particles. The first colligative property that we will study today is the relative lowering of vapor pressure. So whenever we add a solute which is non-volatile in nature, it results in the lowering of vapor pressure. Now, Rawls established the lowering of vapor pressure, which depends only on the concentration of solid particle, and it is independent of their identity. So what is that relation? So it is between the mole fraction and the vapor pressure of the solvent. We know this equation from the Rawls law, that P1 equal to chi1 P1 naught. Further, we can substitute 1 minus chi1 as chi2. On doing that, our equation reduces to this form. Clear? So this is basically the transformation of putting chi2 as 1 minus chi1. Now, in a solution which contain a numerous number of non-volatile solutes, the lowering of vapor pressure is the sum of the mole fraction of different solutes. This can be written as delta P1 by delta P1 naught equal to chi2. So here the term written on the left hand side, which is delta P1 by P1 naught, is the relative lowering, because the upper one is the lowering and we are calculating it with respect to the pure solvent. For that reason, we call this term as the relative lowering, and it equal to the mole fraction of the solute, which is non-volatile in nature, and we have added to the solvent. So the expression on the left hand side of the equation can be called as the relative lowering of vapor pressure, and it is equal to the mole fraction of the solute. Now, this equation can be written further as the number of moles of the solute, which is N2, divided by the total number of moles, which is N1 plus N2. In the place of lowering of the vapor pressure, we have written it as the vapor pressure of the solvent minus the vapor pressure of the solution after introduction of the solute particle. Clear? So, as I have said you that N1 and N2 are the number of moles of solvent and solute respectively. Now further, most of our solution that we will deal with will have a very less amount of solute added to the solvent. So, we can neglect N2 in the denominator. If we do so, then our equation becomes P01 minus P1 by P01 is equals to N2 by N1. Now, what is N2? N2 is the number of moles of solute which can be given by given weight of the solute by molecular weight of the solute. Same thing can be said for the solvent, where we can write the given weight of the solvent by molecular weight of the solvent. So here W1 is the weight of the solvent, W2 is the weight of the solute, M1 is the weight of the molecular weight of the one which is solvent, and M2 is the molecular weight of the solute. So these are capital M, okay? Now, if we know each and everything apart from this molar mass, then we can calculate the molar mass of the solute. So in this way, we are achieving our main aim, which was to know the molar mass of the solute particle. So we know what is the amount of solute that we have added. Same thing can be said for the solvent, and we have taken a solvent whose structure and molecular mass is already known. Then we have calculated, or you can say measured, the pressure using the experimental methods. Then finally we can go and calculate the molecular weight of the solute. Now, moving on to the next colligative property. We know that the vapor pressure of any liquid increases with increase of temperature due to increase in number of particles. So, when will the boiling occur? The definition of boiling goes like this, that if your vapor pressure of the solution becomes equals to the atmospheric pressure, which is 1 atm, then the temperature will be termed as the boiling point. So any liquid will boil at that temperature when its vapor pressure will be equal to the atmospheric pressure. Suppose if I take the example of water, then water boils at 373.15 Kelvin or 100 degrees Celsius. It is happening at this temperature because at this temperature your vapor pressure of the solvent becomes equals to 1.013 bar or 1 atm. As a result of this equal pressure, now the liquid particle can push through the atmospheric pressure and move on to the vapor phase. So you can think of the liquid particles trapped inside because of the existing pressure, which is the atmospheric pressure. But as soon as this pressure is released, your solid particle or your water particles will escape into the atmosphere. Okay. So when we add a solute which is non-volatile in nature, like your sucrose, then your boiling point, what it increases? It is increasing because now there are less number of particles which are capable of going into the vapor phase, as the surface is also covered by the sucrose particle. Therefore, at 373.15 Kelvin, we have a pressure which is lower than 1.013 bar. So now in order to make it boil, we have to move to a higher temperature so that your temperature becomes self-sufficient to increase the vapor pressure of the water molecules, which can be equal to the atmospheric pressure. So we can finally conclude that if we add a non-volatile solute to a solvent which is having a boiling point, then its boiling point will increase on this addition, and this phenomena is called as elevation of boiling point. The phenomena is occurring because of the introduction of solid particle onto the surface, which decreases the exposure of solid particle onto the atmosphere. To understand this in a much better way, we can look at an example. You can see it here that when we are increasing the temperature, then for the pure solvent and both for the solution, you can see that the vapor pressure is increasing. But the problem here is that your vapor pressure should increase such that it equals to the 1 atmospheric pressure. But due to backward starting of this solution, okay, you can see that it is reaching the atmospheric pressure at a much greater extent or at a greater temperature. So you can see that T0B is the boiling point of the pure solvent and TB is the boiling point of the solution. Therefore, there is a gap between these two, which is your elevation amount. Why it is happening? Because solvent already has a greater vapor pressure due to its more volatile nature. Therefore, it reaches this 1 atm bar, which is this bar, much easily and boils first. Now, similar to the lowering of the vapor pressure, the elevation of boiling point is also dependent upon the number of solid particle. So, we can call it as the colligative property. So, it doesn't matter whether we are adding sucrose or any other non-volatile particle, the water will now boil at 373.52 Kelvin at 1 atmospheric pressure. So, the pressure is important here because we have to reach this bar. Now, suppose we try to define the formula for it, then we can write delta TB, which is the amount of elevation, equals to the boiling point of the solution minus the boiling point of the pure solvent, which is T0B. The experiments have shown that for the dilute solution, the delta TB is directly proportional to the molar concentration of the solute in a solution, or it is delta TB is directly proportional to the molality. This can be represented with the help of the equation, and then we can remove the proportionality sign with a proportionality constant, which is Kb. What is this Kb here? Kb is called as the boiling point elevation constant, or the molar elevation constant, or the ebullioscopic constant. So these are the three names. So you should remember all of these three, as anyone can be used in your exam. We know it very well. Molality is the amount of or the moles of solute which can be dissolved in 1 kg of solvent, and this is equals to kbm. What will be the unit of kb? It will be Kelvin kg per mole. Remember, this kb is defined for solvent and its value will change whenever we change the solvent. And if we are not changing the solute, then we don't have to worry about the kb value as long as the solvent is same. So if we are dissolving the salt in the water or the sugar in the water, the kb value will remain same, and it is dependent upon temperature. Now suppose we have W2 gram of solute dissolved and the molar mass is M2, and this amount of solute is dissolved in W1 gram of the solvent. Then the molality can be given by W2 by M2 by W1 by 1000. So we have to convert this gram thing into 1000 into kilogram by dividing it by 1000. So we got this equation of molality. Now substituting it back into our previous equation, which was delta TB equal to kbm, we will get delta TB is equals to kb into 1000 into W2, which is the weight of the solute, divided by the molecular mass of the solute multiplied by the weight of the solvent. Remember, this weight of the solvent is converted into kg by dividing by 1000. So if it is already in kg, you don't have to take this 1000 factor in your final calculating equation. But what are we interested in? We are interested in the molecular weight of the solute, which is capital M with a subscript of 2. We will cross multiply our equation further to get our required equation for the molecular weight of the solute. Hence, we can say that if we want to determine the molecular weight of the solute, we can do it by experimentally defining the delta TB, which is the change in elevation point, and it can be done very easily with today's scientific advancement. But why are we doing it for the solid particle? We can do the spectrochemical analysis because this process is much easier. Moving on to our questions. Question says that the vapor pressure of pure benzene is 0.850 bar. Then we are adding a non-volatile, non-electrolyte solid which weighs 0.5 gram. Now this amount is added to 39 gram of benzene. We have to calculate the molar mass of the solid substance. The molar mass of benzene is given as 78 gram per mole and the vapor pressure of the solution is given as 0.845 bar. How we will calculate it? So the quantities that we know should be noted down first. We know the pure solvent's vapor pressure. We know the solution vapor pressure. We know the solvent's molecular weight. We know the solvent's weight and the solute weight. Now this is clearly an example of relative lowering of the vapor pressure. So we will substitute our values in the same equation. If we do so, we will get the value of relative lowering as 0.850 bar minus 0.845 bar divided by 0.850 bar. So we have taken 39 gram. If we do the calculation, we will get it as 170 gram per mole. Okay. So this will be 170 gram per mole, our final answer. Then moving on to the next question, we have 18 gram of glucose which is dissolved in 1 kg of the water in saucepan. At what temperature it will boil? At 1.013 bar if the Kb is 0.52 Kelvin kg per mole. So this is an example of elevation of boiling point. Moles of glucose will be 18 gram. So its molar mass will be how much? 180 gram per mole. So we can divide this two to get the number of moles. This will be equals to 0.1 mole. Then what is the solvent's mass? It is 1 kg given in the question. And the molality of the solution is also given. It is 0.1 mole per kg. Now, what is the change in boiling point? We will use our equation delta TB equals to kbm or 0.52 Kelvin kg per mole. It is given here kb value multiplied by the molality which is 0.1 mole per kg. If you calculate this, you will get 0.052 Kelvin. Now, since your water boils at 373.15 Kelvin, your new boiling point will be 373.15 plus 0.052. Therefore, your final temperature which is required for the boiling of the solution is 373.202 Kelvin. Our next question, the boiling point of benzene is given 353.23 Kelvin and we are adding 1.80 grams of non-volatile solute to 90 gram of the benzene. The boiling point is being raised to 354.11 Kelvin. Now we have to calculate the molar mass of the solute if the Kb is 2.53 Kelvin kg per mole. So Kb is given for the benzene solvent. To solve it, we will again use the colligative property of elevation in boiling point. The elevation in the boiling point can be given as 354 minus 0.11 minus 353.23 Kelvin. So we have it here, the boiling point of benzene, and we have the new boiling point. Therefore, we can get the elevation from here. By doing the subtraction, we get 0.88 Kelvin. Now, our equation for the calculation of the molecular mass of the solute is 1000 into W2, which is the weight of the solute, multiplied by the ebullioscopic constant, divided by the elevation in boiling point, multiplied by the weight of the solvent. If you put all these values, and you have it also, 0.88 is being calculated here, and 2.53 is the Kb value given. Mass is given as 1.80 grams. We have to convert this thing into kg. So we have to multiply it by 1000. What is being converted? The mass is converted. Okay. Divided by 0.88 Kelvin and 90 grams. Okay. What it will give you? It will give you the molecular mass of the solute. Now we are multiplying it by 1000 to convert this mass into the kg thing. If you do this calculation, your molecular mass will come out to be 58 gram per mole. Therefore, we can say that M2 is equals to 58 gram per mole. So this was all for the theory lecture. Thank you for joining our session.